Okay, folks. So far we've covered the idea that food webs are like big sets of interactions, right? That we had previously thought about these bipartite networks where we're thinking about plants and pollinators, or plants and herbivores, or carnivores and their prey. But that in actuality, ecosystems are sort of nested in a larger set of interactions that we call food webs. And we can use food webs to understand all sorts of things about ecosystems. We can understand things like how energy moves through an ecosystem. We can understand how the relative allocation of biomass to different trophic levels, these trophic levels are measured as their distance from the autotrophs that produce energy, how biomass through very different trophic levels sort of changes, and it can tell us things about population rates. For example, high turnover in marine ecosystems can lead to sort of these inverted biomass pyramids, right? And then we talked a little bit about what controls the shape of those energy and biomass pyramids, right? That trophic efficiency, the rate at which prey are consumed, assimilated, and then turned into biomass is different among different ecosystems. And your book went through a bunch of examples that I'm sure you read right after the mini lecture among different kinds of organisms, right? It mentions that invertebrates, for example, have really high production efficiencies, and really small endotherms have very low production efficiencies. And now we're going to talk a little bit about change in these food webs, change in these networks of interactions. So the central question of this mini lecture, is trying to answer is like, what limits net primary productivity in an ecosystem? We skipped chapter 20 in this book, but chapter 20 talks a lot about production. And net primary productivity is still a thing I want you to know. This is the amount of carbon assimilated from the sun by a ecosystem. Net primary productivity. How much carbon can we store as biomass? We're not going to talk a lot about super applied ecology. We sort of ran out of time here, but a lot of folks in our department are really interested in this question. And generally, as a society, we're really interested in how can we control how much carbon is stored in ecosystems? Because this is changing all the time, right? When we burn down forests, we lower their biomass, right? Forests have really huge, wide biomass pyramids, right? Where so much of the biomass in trees is not converted into herbivores. Whereas, grasslands, for example, have much narrower biomass pyramids. Less of that carbon is stored, less of that biomass is stored in lower trophic levels. And the central question of this mini lecture is, what shapes net primary productivity? You might imagine two sets of things. You could imagine that, for example, the amount of sunlight, the amount of water, the amount of nutrients in the soil is what limits how many plants can grow. And that limit on how many plants can grow limits how many herbivores can live there. And that limit on how many herbivores can live there limits predators and carnivores, right? We would call that bottom-up control. So that's the first main idea in these notes is bottom-up control. And bottom-up control states that basically nutritional and abiotic limits to plant growth are the main limiting factor for net primary productivity in an ecosystem. Alternatively, you can imagine another situation called top-down. We've talked a little bit about this, especially in our herbivore and carnivore examples, our mini lectures, when we talked about the landscape of fear. But you can imagine another situation, right? Where rather than plant growth being limited by the amount of nutrients available or plant growth, instead it's limited by herbivory, right? That there are so many, let's say there's a lubber outbreak. If you guys can get out this week to Arthur R. Marshall, Loxahatchee, do your last few observations out there, you'll see that the lubbers are just coming in. They're getting big, these big caterpillar or big grasshoppers. And there's tons of them, or maybe there's Mormon cricket outbreaks in the West. And they are roving through the desert, eating every plant, right? In this case, what's limiting net primary productivity is herbivore abundance. And probably what's limiting herbivore abundance in some cases is a lack of enough predators and enough of those predators eating those predators, right? And we call that top down. So we could imagine a situation then that we could test, right? Where we say, let's change the relative abundance of one trophic level and see how it impacts biomass or energy accumulation at all the others. And we could call this a trophic cascade. This is an important idea. How changes in density, changes in biomass or density, if we're working in a spatial context, at one trophic level cause changes throughout an entire food web. The trophic cascade. These are changes at one trophic level, move to another trophic level. And we could imagine two situations then when we think of these as trophic cascades, where primarily the changes cascade upward. So we're looking at here a biomass pyramid, circles instead of bars. And changes in plants really have strong effects on the biomass of herbivores, and that has a strong effect on the biomass of a secondary consumer, and that has a strong effect on the biomass of a secondary consumer. Alternatively, you can imagine a situation where, let's say, a wolf, for example, right? A wolf eats a elk, and changes in abundance of wolves cause a strong change in how well this herbivore, the elk, consumes its food. It changes its trophic efficiency. Probably not by, changing the rate at which it converts energy into muscle, right? Because that's a physiological process mostly driven by endothermy, but instead changes consumption efficiency, right? The elk spends much more time being vigilant, being afraid of the predator, looking out for itself and its young, and spends a lot less time eating. The consumption efficiency that we learned about in the previous mini lecture would go down. And so that in that case, that would cascade to have a positive impact on plants, right? Positive impact on plants. So this would be called bottom-up control, and this is top-down. And one of the key concepts in ecology is that these processes can be happening simultaneously, right? These processes on varying temporal and spatial scales can be happening simultaneously. So there's this adage that only one thing can limit the rate of reaction, right? And that's pretty much true, right? Like if there's not enough nitrogen for a plant to grow, then top-down effects can't happen, right? So let's imagine a situation here where we have this plus sign. If a carnivore eats more of the herbivore, that actually let's call this a minus sign. If a carnivore has a negative effect on an herbivore, that would have a positive effect on a plant. But if there's not enough nitrogen, no nitrogen, then that top-down effect can't happen, right? Maybe this biomass is already where the nitrogen limit can support it. And that's true for an ecosystem, right? Like only one thing can limit the rate of net primary productivity at a time, or maybe two things if they have exactly the same limit, right? But it's very rare that more than one thing limits the rate of a given thing. But that doesn't mean that at varying spatial and temporal scales that both of these things aren't likely in play in every ecosystem, right? In most cases, in most ecosystems, we're going to see some effect of bottom up and some effect of top down limits on net primary productivity because all of these interactions are happening simultaneously, right? The other thing that this chapter emphasizes, so far we've talked about really simple systems. I'm talking about maybe like 3 trophic levels, an autotroph, a primary consumer, secondary consumer, or maybe we add a tertiary consumer on top. But like we talked about, real food webs, much more complex, right? We have varying trophic levels. We should make it actually look like a real food web where, it's less dense at the top. But then we also have omnivores in here, maybe even eating across trophic levels, right? And then we have some, top predator here eating these things. The evidence for top-down and bottom-up limits on net primary productivity, on these trophic cascades that we have talked about, has mostly been seen in simple systems like this, where we have relatively low diversity, relatively high levels of sort of linear food webs. We know a little bit less about trophic cascades in more complex food webs, right? And this would even still be a simple food web. Right? We're only talking about, 5 or 6 plants, 2 or 3 herbivores. You know that that's a simple ecosystem because you've been out looking at them in South Florida. And so it's important to note that like you can imagine that in some, if we cut off a part of this, let's pretend like we're only looking at this part of this food web, that we could see very clear top-down effects. But if we looked at a whole part of it or another part of this, that we might see bottom-up effects, right? And so it all depends on the context and the reading frame, sort of like what part of the ecosystem you're looking at. And that's why sort of even though only one thing can limit the rate of a reaction at any given time, that in a real ecosystem, this is sort of in flux temporally and spatially. So the important ideas here are that like both top-down and bottom-up processes are quite common in nature. They can both happen at the same time. And these trophic cascades are also common, right? That the interconnected web of ecology means that like changes in the abundance, in the biomass, in the population rates, all these things we've learned about up to this point, in one trophic level can move across a food web and cascade and have effects across the food web. Awesome. Okay. Let's keep it moving. In the next mini lecture, we're going to talk about some case studies for these trophic cascades.